Okay, so let's go through the solution to problem 9 on our practice test. Let's go ahead and read the problem. A hiker throws a stone from the upper edge of a vertical cliff. The stone's initial velocity is 25 meters per second, directed at an angle of 40 degrees as measured with respect to the cliff face. The stone hits the ground 3.75 seconds after being thrown and feels no appreciable air resistance as it falls. Then in part 1 of the problem, we're asked, what is the height of the cliff? Alright, so this is a projectile motion problem, and we're going to go ahead and utilize our problem-solving strategy to find the solution. Let's first define a coordinate system. I'm going to arbitrarily choose the point where we're throwing the rock from to be my origin, and I'll define the plus x-axis to be horizontal. I'll define the plus y direction to be vertical, pointing straight up, and then that means the minus y direction is straight down. Okay, so I've defined my coordinate system. I had to do that first because we're going to be using concepts of velocity and acceleration in this problem. Those are both vector concepts, and for vectors to make sense, we must have a plus x direction and a plus y direction, for example. Now let's go ahead and use the next step in our problem-solving strategy, which is writing down the knowns. What is given to us in the problem? Right? We know that the initial velocity is 25 meters per second at an angle of 40 degrees with respect to the cliff face. So that's telling us that the magnitude of the initial velocity is equal to 25 meters per second. And it's telling us again that this angle, as measured with respect to the cliff face, is equal to 40 degrees. So we know the magnitude and direction of our initial velocity. They also tell us in the problem that the time in the air is equal to 3.75 seconds. Okay, that's going to be important to know. So that's everything they told us, but we have some more knowns. First of all, we've defined our initial position in x and y to be equal to 0, right? Because we defined our origin to be where we're throwing the rock from. So because of that, I can say x naught, my position in x at time equals 0, is equal to 0, and y naught, my position at time equals 0, and y is equal to 0. All right, so that's two more knowns. And then finally, we can bring two more knowns into this problem based on our conceptual knowledge that we're on Earth, and on Earth, any object that is in free fall, any object that has no other forces affecting it besides gravity, is going to have acceleration in the y direction equal to minus g. Right, we know the acceleration near the surface of the Earth is g, or 9.81 meters per second squared, and I'm going to define that to be negative because I've defined down to be negative in this problem. Right? We also know that the acceleration in the x direction has got to be 0. Right? We know that because this object is in free fall, there's no air resistance. So once this stone leaves the hiker's hand, there are no other forces affecting it besides gravity, which is only in y. Right? So there's nothing that can cause acceleration in x, and so whatever component of the velocity it starts with in x, it's going to have throughout this motion. Okay? And so we now have all our knowns. We can now start thinking about what concepts can we use to solve this problem. And these knowns we just wrote down are going to be the most important conceptual clues here. The acceleration in x is equal to a constant, or 0. The acceleration y is equal to a constant, negative g. So the fact that these are constant tells us that we can understand a lot about their motion. Namely, we can use the constant acceleration kinematic equations to solve this problem. Right? So that's going to be the kind of key conceptual step we have to make. In order to do that, let's first manipulate our given knowns just a little bit more. That is, we know the initial speed and direction of our rock, but we don't know the components of that velocity along x and y. And since we know that the motion in x and y is going to be different, that is, the component of the velocity in x is not going to change, where the component of the velocity is going to be increasing in the negative direction as this object falls, right? It's going to be speeding up and speeding up and speeding up as it falls. It makes sense to split this problem up into motion in x and motion in y. And so let's go ahead and do that. We can define this to be the component of the initial velocity in the y direction, and this to be the component of the initial velocity in the x direction. I now have a triangle where I know the hypotenuse is 25 meters per second, and I know this 40-degree angle is a right triangle, so I can use my trigonometry to see that the x component of that velocity is equal to v naught times now I'm going to use sine of 40 degrees because that is opposite that 40-degree angle. So we have to be really careful with this. You get kind of in the habit sometimes of using cosine to find x components, but the way this problem was defined, this angle is kind of a strange angle, and we have to use sine to find the x component. So never blindly use cosine or sine. Always draw the triangle and use your trigonometry to figure out the solution. All right, so we know v naught is 25, so we can plug that into this equation, and we find the initial component of the velocity in the x direction is 16.1 meters per second. We can also find the the y component of the initial velocity, and see that that is adjacent to that 40-degree angle. And so it's going to be v naught times cosine of 40 degrees, because cosine is our trig function for adjacent, remember SOHCAHTOA. And I'm going to put in a minus sign here. Right? I'm going to recognize that the way I've defined my coordinate system, this component of the velocity is definitely in the minus y direction. So I'm going to put in that minus sign by hand. And so I can now plug in and write down that the initial component of the velocity in the y direction is equal to minus 19.2 meters per second. Okay, now we definitely have all our knowns, and we've done this little bit of setup. This is the first step you always want to do when trying to solve these problems, is figure out what the x component of the velocity is in x and y. Right? Break up any vectors into x and y components. That's going to be important to solving the problem. Okay, now that we have all these down, we can think about using our conceptual knowledge that we have constant acceleration, and we can look at our constant acceleration equations and think about which one is going to be relevant to solving the problem. And we can see that one of the equations, namely this one, y is equal to y naught plus v naught yt plus 1/2 at squared, is going to be helpful to us because it has everything known except for our one unknown. We know that our initial position y is 0. We know our initial velocity in y. We know the time in the air. We know the acceleration in y is equal to minus g, and again we know the time. So our only unknown in this problem is y, or the final position of this object in y when the rock hits the ground. Right? So if I can figure out that, I'll call that y final here, and I can maybe label this y final also. If I can find y final, then I can recognize that the height of the cliff is going to be given by h is equal to the magnitude of the displacement of this object in y. If I know y initial and y final, I will know the height of this cliff. So that's a good thing. So now that I recognize this is the equation we want to use, and we have one unknown and everything else known, we can just plug in. All right, we're ready to start solving. So y final becomes equal to v naught y, which is equal to minus 19.2 meters per second, times t, which is 3.75 seconds, and then we have plus 1/2 times acceleration in y, which is equal to minus g, times t squared, which is 3.75 squared. Okay, and we plug this into our calculator, and we find that the final height of this object is going to be equal to minus 141. 141 meters. And so now we know the final position of the ball on y, and we know what the height of the cliff is, right? We can see again that the height of the cliff is going to be equal to the magnitude of the displacement of this object in y, so that's y final minus y initial, and y initial is 0, y final is minus 141 meters, so the height of the cliff must be equal to 141 meters. And so we have our answer to part 1 of this problem. So that's great. Let's go ahead and solve part 2 of this problem. How far from the foot of the cliff does the stone land? Okay, so that's asking what is the final x position of this stone. We want to find this, x final. How far away from the foot of the cliff does the stone land? Right? We want to find this distance. So let's go ahead and think about that. First, we'll write down our unknown is equal to x final. It's good to write that down in symbolic form. And we've already written down all our knowns and unknowns. We know a lot about this problem. And so we can think about our concept. Our main concept here is this one. The acceleration in x is equal to 0. That means that we can use constant acceleration equations, and we can use a very similar constant acceleration equation. That is, this time in x final is equal to our initial position in x plus the initial velocity in x times time plus 1/2 the acceleration in x times time squared. And recognize that the acceleration in x is equal to 0, so that term just goes away. We define the initial position to be equal to 0 in x, and so our final position along x is just going to be velocity times time, right? If we're traveling at 60 miles per hour for an hour, we go 60 miles, right? So this is simplifying to a relatively simple formula because we have 0 acceleration in the x direction, we have constant velocity in x. So we can just now go ahead and plug in. V naught x we found already to be 16.1 meters per second. The time they told us in the problem is equal to 3.75 seconds. Right? How far this object goes in x depends on the component of the velocity in x and how long this object is in the air for, and it's in the air for 3.75 seconds. So we plug in to our calculator and we find the answer to be 60.4 meters. And so we have finished the problem. So please let me know if you have any questions.